So, and I'm glad to see everybody on the talk of Peter Sandon from KU Leuven, who will tell us about the R-infinity property for right-angle Tartan groups, which are also called graph groups or partially commutative groups.
Indeed.
So, yeah, please, Peter, the floor is yours.
Okay. Thank you, Timur. So I will only be talking about right-angle Tartan groups. This is terminology I stick with. So indeed, I will be talking about the R-infinity property for right-angle Tartan groups today. So last time, 2 weeks ago, I discussed a dictionary between the graphs and the groups to see how certain graph properties translate into group properties and vice versa. And the goal of today is to discuss this R-infinity property and see how we can use this dictionary in order to prove it for certain cases. But first, I will give some topological motivation for this notion of R-infinity property before I truly introduce it. So topological origin is from counting fixed points on topological spaces. So given a topological space, let's say, for example, a torus and a map F between it, so continuous, and we're interested in the number of fixed points it has. And one way of determining the number of fixed points is by looking at the universal cover of your space. So in this case, the Euclidean plane, R squared. So this map F will lift to a map F tilde. So a lift means that the diagram here commutes. So first projecting and then applying F is the same as applying your lift on the universal cover and then projecting down. But of course, there are multiple lifts here above. But for each of these lifts F tilde, we can look at the set of fixed points. And by the commutativity of the diagram, fixed points of F tilde will map down to fixed points of F. So if we have all information about the fixed points of the lifts, we will probably get all information about the fixed points of F. But there are some lifts here above that are in some sense equivalent, namely that they will yield the same set of fixed points after projecting. And the ones that are the ones that are conjugate by means of a covering transformation of your universal cover. So a homeomorphism of your space that commutes with the projection in some sense, that respects the projection, so to speak. So if two lifts are conjugate by means of such a covering transformation, then their fixed point sets will map to the same on the level of your torus. And if they are not conjugate, then their fixed point sets will be disjoint. So the fixed point set of F will be or can be written as a disjoint union of these projections, where you take the union over all conjugacy classes of these lifts. So lifts up to conjugacy under the deck transformation or covering transformations. So indeed, we will get every fixed point of F as an image of a fixed point of a lift. So this closely resembles a partition, but it's not a true partition, since it can happen that such a fixed point set of F tilde is empty. So in a partition, every element is non-empty, or every set is non-empty. Here, it can happen that a lift doesn't have any fixed points. Now, related to this disjoint union, we define the topological Reidemeister number simply as the number of lifts up to conjugacy. So, and this gives some very crude estimates on how many fixed points there are, because every lift with a non-empty fixed point set will yield at least one fixed point here. So there is some relation between the topological Reidemeister number and the number of fixed points, but not very concrete. But in some situations, you can make this more explicitly, and I will come back to this later. So we've moved our problem from counting fixed points here to counting fixed points or fixed points classes here above with this topological Reidemeister number and looking at these lifts. But this is still quite a difficult problem, because we have, first of all, to determine these lifts and determine the action. So we want to translate it into a bit more feasible problem. And to do that, we use the following observation. So if we fix a lift F0 tilde of F, then all lifts of F are left translates of this fixed lift, where we translate by an element of the covering transformation group. So every lift will be of this form. Now, here we use left translates. We can do the same by right translates. Every lift of F is a right translate of this fixed shift F0 tilde. So combining them, we can write each right translate as a left translate, but the deck or the covering transformation we use to translate on the right is not necessarily the same as the one we use on the left. So this is why this map phi f tilde 0 appears. So this map phi for short is a map on the group of covering transformations, and it will be in fact a group homomorphism. So it behaves nicely with respect to group composition. And with this map f, with this map phi, sorry, we can determine this conjugate relation more easily. So two lifts of f, which can be written in this way. So left translates of f tilde 0 are conjugate, if and only if their translating parts, so alpha and alpha prime, are related in the group of covering transformations in this way. So gamma composed with alpha prime composed with phi applied to gamma inverse. This follows if you work out the concrete expressions, you will get this. So this translates this problem of determining equivalent lifts up to conjugacy into a purely group theoretical problem, namely determining the number of equivalence classes under this relation, because this type of conjugacy relation with given phi is in fact an equivalence relation. So this is an algebraic way of defining or counting the topological Reidemeister number. So by definition or by equivalence, this equality holds. This is this equivalence. So we've reduced it to an algebraic problem. Now, still on the group of covering transformations is quite difficult because it's difficult, first of all, to determine the universal cover of an arbitrary topological space, and to then compute its group of covering transformations. This can take some work. But there is another group related to a topological space, namely its fundamental group. And on this fundamental group, we have a very easy induced map, namely F star. So the induced map on the topological, on the fundamental group. And so with F star, we can do the same definition. So two elements in your fundamental group are related or equivalent if this relation holds, but then with F star instead of phi. And in this way, we get what we call the algebraic Reidemeister number, since we just defined it in terms of algebra on the level of groups. And it would be nice if the algebraic one and the topological one coincide. Now, we know the group of covering transformations and the fundamental group are isomorphic. And our hope is that this isomorphism makes this diagram commute, and this will be the case. So this diagram commutes, so the topological Reidemeister number will be the same as the algebraic Reidemeister number. And so to determine this algebraic Reidemeister number, we essentially have to work on the fundamental group, but it's often easier to compute the fundamental group and this induced map on it than to determine the group of covering transformations, and especially this map phi of f tilde 0. So this reduces the problem quite substantially. And so algebraically and topologically, the Reidemeister numbers are the same. Now, why do we want to compute these Reidemeister numbers in relating to the number of fixed points? So in general, this gives some information on the number of fixed points, but not full. But there are situations, for instance, on nil manifolds, so topological manifolds with a certain condition on the fundamental group. I think it has to be torsion-free and nilpotent, but I'm not entirely sure if this is the right definition of nil manifolds. But just to give an example, on some class of manifolds, the Reidemeister number gives full information. Namely, if the Reidemeister number of your map F is finite, so either the topological or the algebraic one, since it's the same, then this Reidemeister number equals the minimal number of fixed points of a map homotopic F. So this means that whatever map F, whatever map G that you take that it's homotopic to F, it has at least R of F fixed points. And this minimum is in fact achievable. So there is a map homotopic to F with exactly R of F fixed points. This is if the Reidemeister number is finite. If it's infinite, then this minimum is equal to 0. So you can find a map homotopic to F with no fixed points. So on this class of topological spaces, Reidemeister numbers give us complete information about fixed points. And up to homotopy is the best thing we could hope, because in topology, everything is defined or useful up to continuous deformation. So it should be no surprise that in these lower bounds or expressions there comes some continuous deformation. Okay, so this has a sort of motivation or origin where these notions or Reidemeister come from, and let me now head to really define them in some sense in an algebraic setting and what we are interested in for the rest of the talk. So we lose the topological context and just work on the level of groups. So given a group G and an automorphism, so everything up until now can work for endomorphisms of groups, and everything I will say works to some extent for endomorphisms. But for this talk, I will mostly be interested in just automorphisms. So given an automorphism, we define two elements of our group phi conjugate if this relation holds for some z in our group G. And this is precisely this sort of twist conjugacy relation that we saw earlier in the lifts of our continuous self map. So we will denote it in the following way with a curly squiggle with the sum index phi. And it's also called twist conjugacy, as I said, because if you take phi to be the identity map, you get the regular notion of conjugacy in groups. So it's a generalization of regular conjugacy. And as before, the Reidemeister number, R of phi, is defined as the number of phi conjugacy classes. So this is an equivalence relation, or you can also see it as a group action. So you count the number of orbits or the number of equivalence classes. It's the same. So these notions are the same as before. And then on a group theoretical level, they've also defined the Reidemeister spectrum. So it's a set of all Reidemeister numbers of automorphisms. So this is a subset of the natural numbers together with this number infinity. And this number infinity gets some special attention because, well, we say that the group G has the R infinity property if this Reidemeister spectrum only consists of the singleton infinity. So if every automorphism has infinite Reidemeister number. And as a shorthand notation, we also use G is element of R infinity. Now, why does an R infinity property? In 1994, Alexander Felschen and Richard Hill posed the question to determine which groups have the R infinity property. Because, for instance, going back to the null manifolds, if your fundamental group has the R infinity property, then any self-homeomorphism of your topological space is homotopic to a continuous map with no fixed points. So you get some information regarding your topological space or maps on your topological space. So this is one way you could modify this. Otherwise, it's just also the intrinsic motivation. You have a certain group property, and then it's always the question which groups have this property and which don't, and can you somehow classify these and give some general conditions that have to be satisfied in order for a group to have the R infinity property. But besides the R infinity property, there is also some interest in determining Reidemeister spectra of specific families of groups for which it's either known that they don't have the R infinity property, or in order to prove that it either has or doesn't have the R infinity property. Okay, now definitions are all well, but let me just give an example on how to work with these Reidemeister numbers. So let me look at the free abelian groups of finite rank. So take an automorphism phi, and if you then apply the definition of phi conjugacy, we get this. So x is equal to a plus y minus phi of a. Now in abelian groups, we can move around our elements quite easily. So we can move y to the left-hand side. And then the condition boils down to the fact that x minus y must lie in the image of the difference of the identity map with phi. So the number of phi conjugacy classes is the same as the number of cosets of this set in Z to the n. So the Reidemeister number is the size of the co-kernel of this map. And for the size of the co-kernel, there is an explicit expression. This is equal to the absolute value of the determinant of your map if the determinant is non-zero. And if it's zero, this determinant, then the co-kernel has infinite size. So this gives us an explicit way of computing Reidemeister numbers on free abelian groups. And as a corollary, you will see that your automorphism phi has infinite Reidemeister number if and only if phi has an eigenvalue 1. And this observation is useful later on, that to prove that it has infinite Reidemeister number essentially comes down to a linear algebra problem, namely determining its eigenvalues and see that it has eigenvalue 1 or not. So this will come in handy later. And for the sake of completeness, I've put here the Reidemeister spectrum of free abelian groups, since free abelian groups are special cases of right-angled Artin groups. So to determine its Reidemeister spectrum, we also have to consider these cases. So for a free abelian group of rank 1, so just an infinite cyclic group, it only has 2 elements in its Reidemeister spectrum, 2 and infinity. But from the moment your rank is at least 2, you can get every natural number, except 0, of course, together with infinity as a Reidemeister number. So this is also called a full Reidemeister spectrum, since it's the biggest possible set that can occur as a Reidemeister spectrum. Okay, so this is a sort of example on how we work with Reidemeister numbers. And a very useful tool in the context of our infinity property is the following lemma. And I wrote core lemma because in almost any paper about our infinity property, this lemma will appear in some form because it's one of the most used techniques to prove that it has our infinity. And the lemma is as follows. So you have an exact sequence of groups. So mostly a group G with a normal subgroup and its quotient. And you have an automorphism phi that respects this exact sequence. So it induces one on phi on the subgroup N and thus also one on the quotient. If you are in this situation, then if the induced map on the quotient phi bar has infinite Reidemeister number, then also the map phi on G itself has infinite Reidemeister number. So in particular, if G over N has the R infinity property, and N is a characteristic subgroup, meaning that every automorphism on G induces one on N, then G itself will have R infinity property as well. Why? Every automorphism phi induces one on N, hence also one on G over N. And since this automorphism will have infinite Reidemeister number by the assumption, then by the lemma, phi itself will have infinite Reidemeister number as well. So this is a very common tool that is used to prove that a group has the R infinity property by looking at certain characteristic quotients. And this is also what we will do for right-angled Artin groups. So this is all stuff regarding preliminaries. And I want to say that are specific to Reidemeister numbers and R infinity property. The rest of the preliminaries regarding right-angled Artin groups I've seen last time, so I will recall them as I go through the results to give a sort of reminder on what we did exactly last time. So now for the remaining of the talk, we'll be discussing results regarding our infinity property for right-angled Artin groups. So let me recall, so given a graph gamma with vertices V and edges E, we define the Rag I gamma as the group generated by the set of vertices. And the only relations in our group are commutator relations among 2 vertices that are joined by an edge. So this is a definition of a right-angled Artin group. And then the conjecture my supervisor Karel de Kimpe and myself had, or still have, is that if gamma is a non-complete graph, so there are at least 2 vertices not connected by an edge, then the corresponding right-angled Artin group has the R infinity property. This is still open, spoiler alert, sorry, but we've managed to prove it to some extent. Namely that if it's a non-complete graph on at most 7 vertices, then a gamma indeed has the R infinity property. So we've managed to prove this for all of these graphs. But as we will see later on, we also proven it for several, infinite families of graphs on more than 7 vertices. So this is only one way of quantifying how far we are in proving this conjecture. Now, for those that are interested and want to read about this, I can give 2 references. So these results are published in an article, The R infinity property of right-angled Artin groups in topology and applications this year. But this topic, so R infinity property in right-angled Artin groups, was my master thesis subject in 2019. So in most results, I've written 2021 because this is the official publication datum of this article. But most of the results are dating from 2019 or academic year 2018-2019. But just for reference, because my master thesis is not online available, or not yet, I still have to put it on my personal website. I still have to make my personal website, but I can put it there. So those that are interested can read the article, or I can send you my master thesis if you want it in full detail. Just send me an email or contact me. Otherwise, I will be glad to send it to you. Just to give an indication on the dates and where you have to put it time-wise. Okay. So how did I approach this problem? Well, I start with this. I knew I had the family of all non-complete graphs, and I had to prove it for every graph in this set. Now, by the result of DROMS last time, non-isomorphic graphs yield non-isomorphic groups. So there are as many right-angle Tauten groups as there are graphs, so quite a lot. And my first idea was to reduce this number of graphs I have to consider by using the core lemma. Can I reduce the number of graphs I have to consider substantially, that I only have to prove it for a small subfamily explicitly, and then it follows by the lemma that it holds for all right-angle Tauten groups. So this was the first idea. And as we saw last time, there is one way of moving from a right-angle Tauten group to another one, namely by deleting vertices. A very natural way. If you delete, for instance, the red vertex and all incident edges, then you get another graph. And then on the level of groups, you mod out by the normal closure of the set of vertices. And this quotient group is in fact isomorphic to the right-angled Tauten group corresponding to this resulting graph. So this was one way of moving from one right-angled Tauten group to another one. But in view of the lemma I mentioned, the core lemma, we still have to have that this normal subgroup NOV prime is characteristic, because we want to lift the R infinity property for this group to the one we started with. So we need that this subgroup is characteristic. And I've given some characterization, so a condition or a way of checking if such a subset V prime induces a characteristic subgroup, namely this. No, I won't explicitly need it. So that's why I only gave this short formulation, but I also gave some examples. So I gave the example that if you take all vertices of degree at least a given k, then this will yield a characteristic subgroup of your right-angled Tauten group. And for one specific value of k, this yields a very useful characteristic subgroup, namely if you take for k the maximal degree of your graph. So you take then for V max the set of all vertices of maximal degree. And the useful thing about this is, first of all, it's characteristic by the previous example. And second of all, it will always be non-trivial in the sense that there is at least one vertex contained in this set. Since your graph is finite, there is always a vertex of maximal degree. So we can always divide it out or mod it out on the level of groups. So from A gamma 0, we get A gamma 0 mod this normal closure to contain A gamma 1. Now, gamma 1 contains strictly less or strictly fewer vertices than gamma 0. We've deleted at least one of them. So gamma 1 is a smaller graph. But we can continue in this way. We can delete all vertices of maximal degree in gamma 1 to get gamma 2. Again, it's a characteristic quotient on the level of groups. And we obtain a graph with strictly less vertices. And in this way, we can continue until eventually we'll end up with a trivial group. We've deleted all vertices since our graph is finite. So eventually we'll end up with the trivial group. Now, since each group is a characteristic quotient of the previous one, if we prove, for instance, that A gamma k minus 1 has the R infinity property, then A gamma k minus 2, A gamma k minus 3, and so on up until A gamma 0, all will have the R infinity property. So to prove the R infinity property for all right-angled Tauten groups, I only have to look at which groups appear here at the end. And this was the crucial step in simplifying the problem substantially, hence the name simplification lemma. I only have to see what happens here at the end. Now, here at the very end, from A gamma k to 1, we've deleted all vertices of maximal degree, but we also deleted every vertex. So in other words, gamma k has to be regular. Every vertex has to have the same degree. Now, gamma k is either regular and connected, or it's regular and disconnected. So in the disconnected case, we have some structure, that additional structure we could exploit, namely disconnectedness. But if it's regular and connected, there is this one specific annoying case where it's complete. So that A gamma k is a free abelian group, and these don't have the R-infinity property. So in that case, if it's connected, regular, and complete, we have to move one step back. And then from A gamma k minus 1 to A gamma k, we've deleted some vertices, but not all of them. So again, gamma k minus 1 could be disconnected, but let's assume that it's connected as well. So gamma k minus 1 is connected. It can't be regular because gamma k was non-trivial. So we can't delete every vertex, but moving from gamma k minus 1 to gamma k by deleting all vertices of maximal degree, we get a complete graph. So in the end of our sequence, there is always one of following three types of graphs. There is either a disconnected graph, a connected regular and non-complete graph, or a connected non-regular graph, such that this induced subgraph is complete. And the latter type I call max-bi-abelian graphs. I will explain the terminology in a minute. So the simplification I found is any graph gamma 0 has a characteristic quotient A gamma prime, such that gamma prime is either of these three types. So this reduces the number of cases I have to consider quite a lot, and also gives me more structure to work with. I can now focus on graphs that are either disconnected or have some regularity condition or some other structure that I will explain later on by these max-bi-abelian graphs. Now, as for the terminology, max-bi-abelian, in full, I've coined it maximal degree by free abelian, and this is inspired by the usual terminology or terminology convention in group theory. A group is, for instance, nilpotent by finite if you have a normal subgroup that is nilpotent, such that the quotient group is a finite group. And here the same, we have a normal subgroup generated by vertices of a maximal degree, such that the quotient group is abelian, hence the name max-bi-abelian for short. Okay, so going back to the schematic overview, we have this. So our rectangle has been split up into 4 parts, a gray part, so a disjoint gray part, and then 3 other parts, the part corresponding to disconnected graphs, a part corresponding to connected regular graphs, and one corresponding to max-bi-abelian graphs. So we want to prove the R-infinity property for all groups in this rectangle, but we only have to consider the colored parts because the gray areas can be reduced by taking quotients to one of the middle parts. And to give a more numerical or other way of representing this, this graph represents sort of visual representation of what happens in the simplification lemma. So every blue dot corresponds to a graph on at most 7 vertices, and every arrow going from one layer to the layer below it corresponds to the fact that the bottom graph is a characteristic quotient of the top one. So in total, there are approximately, I think, 1,200 blue dots on this slide. But by the simplification lemma, we only have to consider the blue dots on the bottom. So there are 59 blue dots on the bottom, if I recall correctly. So these 59 graphs are the only one we have to consider to prove that any graph in this picture has the right angle Tartan group corresponding to it with the R-infinity property. So numerically, we went from about 1,200 graphs to 60 graphs, which is 1/20th of the number of graphs we had to consider. So it reduces the number of cases quite a lot. And just for information, the blue lines are in fact parallel. It's just an optical illusion that they seem slanted to the right. They are all plotted on the same height, just as an aside, if people were wondering. So it simplifies things in 2 ways. The number of graphs we have to consider is substantially less, and we have some additional structure. And for the remaining of the talk, it will be seeing which of these structures we can exploit to prove the R-infinity property. So let me start with the first type, the disconnected graphs. So a disconnected graph is in fact a disjoint union of connected graphs, of at least two of them. And recall from last time, a disconnected or a disjoint union on the level of graphs corresponds to a free product on the level of groups. And as it turned out, this is enough structure to prove that the corresponding right-angle Tartan group has the R-infinity property. If the graph gamma is disconnected, then the corresponding graph has the R-infinity property. Now, as for the proof, I won't go into much detail. I'll just mention that it uses the associated Lie ring from last time and the fact that it has this nice presentation by the result due to Papadima and Suciu, namely that the presentation of this Lie ring is visually the same as the presentation of your group. So you can use the same presentation and interpret it as a presentation of a Lie ring. But the full proof is quite technical and with quite a bit of computations. And I won't give it because of two reasons. First of all, it's not something you do in a seminar. And second of all, big generalization was proven sometime later. So it's published in 2021, but the paper appeared on arXiv in the beginning of 2020. And it's the result due to Gonzalez, Sankrang, and Wong, who proved that any free product of finitely many groups under some mild conditions, so the free product has to be maximal in the sense that no factor splits as a free product itself. And you have to have at least two of the factors with the proper finite index characteristic subgroup. So under these conditions, this free product G has the R-infinity property, which vastly generalizes this, because you can check, right-angle Tartan groups are finitely generated and also linear groups. So they are residually finite. So they will have lots of finite index characteristic subgroups. And they are freely indecomposable if you write your graph as a maximal disjoint union, as we saw last time. So your graph splits as a disjoint union, if and only if your group is a free product. So this implies the previous one. And the proof of this is also a lot more straightforward than this one. It uses a bit more elementary arguments than this one. But I would like to mention, because chronologically, this was during my master thesis, so 2019. And this appeared on arXiv a bit later, so they were probably working on this. But to give an indication on time-wise, because based on the dates of the articles, it appears that they occurred at the same time. But the timeline disregarded, we have positive news. We've colored one of the rectangles in our big rectangle green. So all the cases for disconnected graphs are done. So any right-angled Tartan group corresponding to a disconnected graph has the R-infinity property. And by the simplification lemma, some part of the gray area can also be colored green, because these graphs have some reduction to a disconnected case. So if we've made some progress, we've colored a part of our rectangle green. Now, I tried then afterwards to do similar things for connected regular graphs or max by abelian graphs, but I didn't find a general argument to prove the R-infinity property using only these two conditions. So I looked at other situations, other techniques or structures I could exploit. And the first one I looked at is on the level of automorphisms. So recall, the automorphism group of a right-angled Tartan group is generated by 4 basic types: graph automorphisms, inversions, transvections, so maps that map one vertex V to V times W, where everything that commutes with V also has to commute with W. And as a 4th type, we have partial conjugations. Now, intuitively speaking, the transvections make your automorphism group complex because they mix generators in a truly substantial way. I mean, partial conjugations also mix your generators, but it's in a less stringent way than transvections. And then I thought, well, what happens if we leave out the transvections? Can we find graphs which don't admit any transvections at all? The answer is yes. For instance, the cycle graph, this one, does not admit transvections. So in this condition, is not satisfied for any pair of vertices. So for instance, if you take the blue one, its neighbors are the two red ones, and there is only one vertex with these two red ones as neighbors, namely the blue one. So the link, so all its neighbors of the blue one is only contained in the star of the blue one itself. So this graph won't admit any transactions. And the same for the stacked prism graphs on the right, you can check it as well. So this led me to the notion of a transaction-free graph. So transaction-free means that this condition is not satisfied for any pair of vertices V and W. And there was some technical condition I had to add, namely that it's not the graph on exactly one vertex, because for this graph, this condition is trivially true. You only have one vertex, so for any two distinct vertices, this condition will truly hold. So this is for technical reasons, but the positive news was, okay, there exist such graphs, and another family are the connected strongly regular graphs, except the complete multipartite graphs. These are also transaction-free. So I knew that there were infinite families of graphs satisfying this condition. This was first positive element. And the second positive element in trying to investigate these graphs is this one, namely that the family of transaction-free graphs behaves nicely under complements, disjoint unions, and simplicial joins. So I didn't explain the complement of a graph last time. So the vertex set of a complement graph is just the same as the graph gamma itself. And edges in the complement graph correspond to non-edges in the original graph. So any two vertices in the original graph that are connected become disconnected in the complement, and vice versa. Any two vertices that are not connected in the original graph become connected in the complement graph. So these three are transaction-free as well if you start from transaction-free graphs. And as a sketch of the proof, for complement graphs, the condition link of V lies in star of W on the level of the complement graph is equivalent to a similar condition on the original graph with V and W swapped. So if this doesn't hold for any pair of vertices V and W, this won't hold either. So gamma complement is transaction-free as well. For the disjoint union, if this holds in the disjoint union, then V and W must both lie in the same component. Why? Here is where we use the technical condition that neither gamma 1 or gamma 2 consists of only a single vertex, because for a single vertex, the link is empty. It's not connected to any other vertices. So then this would be empty, and then this condition is always satisfied for any W. So this is why we exclude the graph on a single vertex from transaction-free graphs. And then, so this proves that disjoint union is transaction-free as well. And then for simplicial join, you can do it directly as I written here down. But just 10 minutes ago, it occurred to me that you can write the simplicial join as in terms of complements and disjoint unions. Simplicial join is the complement of the disjoint union of the complements, if I recall correctly. So it follows from the first and the second item as well. But you can give a direct argument as well. But in conclusion, transaction-free graphs behave nicely under graph operations. So we have this nice behaving family. And my hope was that, okay, we can prove for this family that it has right angle Tartan groups associated with the R-infinity property. But even more was true. Namely, if you just take the subgroup of automorphisms generated by graph automorphisms, inversion, and positive conjugations. So you can do this for any graph and any right angle Tartan group. Just look at this subgroup. If it happens that it doesn't admit transactions, this is the whole group of automorphisms, but we can just look at the subgroup generated by them. Then any automorphism in this subgroup has infinite Reidemeister number, provided that your graph gamma is non-complete to start with. So any non-complete graph and any automorphism generated by these three types has infinite Reidemeister number. Note that the non-completeness condition is necessary because if you take minus the identity map on a free abelian group, it will have finite Reidemeister number. So this condition is both sufficient and necessary. But this is a very general result because I don't put any restrictions on my graph. I put some restrictions on the automorphisms I consider, but not on the graph. But as a corollary, as I said, if these automorphism groups coincide, if you don't have any transactions, then your group A gamma will have the R infinity property. Now, as for the proof, so based on the fact that it's a quite general result, it holds for any non-complete graph. The approach or the proof will be quite long in some extent, because I only use that we have two vertices that are not connected. But the technique I used is more generally applicable. So the problem we have is we have a finitely generated group G and an automorphism of our group. And we want to prove that the automorphism has infinite Reidemeister number. Now, we can linearize this problem by looking at the induced automorphisms on the factors of the lower central series. So these LIG I introduced last time. And why do I call it linearized? Well, these groups are abelian. They will also be finitely generated. And if moreover, these factors are torsion free, we have free abelian groups. So this is as close you can get to linear algebra as you want in this case. And it has been proven by my supervisor and Daseberg Gonzalez in 2014 that if these quotients are all torsion free and your induced automorphism has infinite Reidemeister number for some index I, then your automorphism phi itself will have infinite Reidemeister number as well. So to find or to prove that phi has infinite Reidemeister number, it's sufficient to find an infinite Reidemeister number on one of the factors. But if these are torsion free, then we have torsion free finitely generated abelian group, hence free abelian groups, finite rank. So we can use this criterion. It has infinite Reidemeister number on the ith factor, if and only if on the ith factor we have an eigenvalue 1. So essentially, the reduction of this problem is from infinite Reidemeister number to an eigenvalue problem. So we have to determine if phi I has an eigenvalue 1 somewhere, if the conditions are met. Now, from last time, I've mentioned the result that these factors are indeed torsion free. And moreover, to find an eigenvalue 1, it's useful to have a nice basis. So it has a nice basis with elements of this form. So vertices with some commutator brackets around it. And the nice thing about this form is that it's, if you apply inversions, graph automorphisms, or partial conjugations, this form is somewhat preserved. Inversions just introduce minus signs. Partial conjugations don't do anything because this is abelian, so conjugation is trivial. And graph automorphisms will just permute these vertices. So we'll get that this is changed into, another expression of this form. But it won't drastically change the occurrence. So this is a nice basis to work in this context. And then the major part is then the hunt for the eigenvalue 1. And this hunt took me till the third factor of this lower central series. So it has a lot of case distinction, but I didn't have to go any further than the third factor. But it took me some, I think 5 or 6 cases that depends on where you can find for the first time an eigenvalue 1. But I managed to do it. So we obtained a new green rectangle in our big picture. So the rectangle of transaction-free graphs. There is some overlap with connected graph, also with connected regular graphs. I don't know if there is overlap with next bi-abelian graphs. So I draw the line here just on the edge. And this green part on the left-hand side has also increased a bit in size for those graphs that can be reduced to the transaction-free case. So, okay, we have a second family of groups or graphs for which the corresponding right angle Tartan groups have the R infinity property. And now let's look for another one. So we've dealt with certain types of automorphisms. Here in disconnected graphs, we had a structure on the group itself. Now the dual of disconnected graphs is the simplicial joint. So dual of free products is direct products of right angle Tartan groups, so corresponding to simplicial joints. And for this family, we've proven a sort of conditional statement. So from last time, any graph gamma admits a maximal decomposition as a simplicial join. So we have some complete graph lying in it, and then a simplicial join of several copies of non-isomorphic and non-complete graphs. So this maximal decomposition was also essentially unique, so unique up to reordering of the factors. And the conditional result we proved is the following. If any of the non-complete graphs gamma j has a right-angled Artin group associated to it with the R infinity property, then this whole direct product of right-angled Artin groups A gamma will have the R infinity property as well. So this result essentially means that we can reduce ourselves to graphs that don't split as simplicial joins. Now, for the proof, it's a bit more straightforward than for disconnected graphs. So Gandini and Weil, recall, gave this expression for the automorphism group in terms of the individual factors. So we had two parts coming from the complete graph KD, and then a third part coming from the non-isomorphic non-complete graphs. So with this automorphism group description, we then did the following. So also recall that the center of A gamma corresponded to all vertices that are connected with every other vertex, but this will precisely correspond to all vertices in k to the power d. By a simplicial join, it's connected to everything here on the right-hand side. And since it's a complete graph, it's connected to all vertices in KD as well. So the center corresponds to the graph KD, and the center is always characteristic. So if we divide it out, we get a new right-angled Artin group whose automorphism group is only given by this direct product. So if we prove it for this quotient group, we're done. But these automorphisms, so the direct product, or let me start with one of the factors in this direct product. So this wreath product means all copies of gamma j are permuted, and on each copy we apply one automorphism. So the copies are permuted but not mixed, and this direct product in front means that non-isomorphic graphs aren't mixed or mapped to one another. So we have a certain we have borders between the non-isomorphic copies. They are not mixed or intertwined in any way. They're just mapped to themselves. So in this automorphism group, if you can prove that any automorphism here has infinite Reidemeister number, we are done. And this is exactly what we did. So if you have any group G with the R infinity property, then any automorphism in of this form, so seen as a automorphism on G to the power n, will have infinite Reidemeister number. Applying this to one of the factors or to the factor that has the R infinity property gives us the result for the quotient of A gamma by its centrum or by its center. And then by the lemma, we can conclude that A gamma itself will have the R infinity property as well. So here we have again a conditional result that we only have to consider graphs that don't split as a simplicial join, or we can use it if we have another type of graph that splits as a simplicial join. Okay, now as for a sort of application, we have the following. So if we take for curly G the smallest family of groups that contains Z, and that is closed under taking finite free products and finite direct products. So just start with Z and, or more general, the free abelian groups and the free groups, and just go haywire with taking finite free products and finite direct products. You obtain the family curly G. Then any non-abelian group in this family will have the R infinity property. Why? So taking free products and direct products corresponds to disjoint unions and simplicial joins. And any non-abelian group in this family will correspond to a simplicial join of disjoint graphs or just a disjoint graph. And in both cases, they have the R infinity property, or the groups will have the R infinity property. Disjoint graphs or disjoint unions correspond to disconnected graphs, so they have the R infinity property. And for the direct products, it's a direct product of groups corresponding to disconnected graphs. So by the previous result, they will also have the R infinity property. So in particular, any direct product of non-abelian free groups has the R infinity property, because the corresponding graph is a simplicial join of co-cliques. So this is the maximal decomposition, and you can apply the previous result on these factors. So this has a nice concrete family of groups that are covered by these results. And just as an aside, to give an idea what I've been doing for my recent research, because as I said, this was mostly topic from my master thesis, and it's been already 2 years. So I've also done some other things in the meantime. Namely, I've generalized to some extent the previous result. Namely, if you take non-isomorphic directly in the composable groups, so groups that don't split any more as a direct product in a non-trivial way, that are moreover centraless, then the same results hold as for right-angle Tartan groups. So your automorphism group will split in the same way. So this is exactly the same decomposition as we had for centralist right-angle Tartan groups. And with regard to the R-infinity property, we even have an if and only if, namely your group G has the R-infinity property if and only if one of the factors has the R-infinity property. So the same you can do for right-angle Tartan groups, but this generalization indicates that the result we had for right-angle Tartan groups does not really depend on the specific structure of a right-angle Tartan group, more on these two group theoretical properties, namely being directly indecomposable and being centraless. So just to indicate that some of the results for right-angle Tartan groups are not restricted to right-angle Tartan groups themselves, but can be generalized to other families of groups as well. But this just as an aside. So back to the schematic overview, we have a new green rectangle. So here I've put it on the left. So there is some overlap with connected regular graphs and with max-bi-abelian graphs, but there is certainly no overlap with disconnected graphs because simplicial join and disconnectedness are quite opposite notions. And also this green shaded area has increased in size. So we've proven it for 3 quite big families of graphs. And so now this was the most I could do for general families. And I then looked at connected regular graphs and max-bi-abelian graphs to see what I could use from the 3 green rectangles I proved already. Now for connected regular graphs, the story is quite short. If you have a connected regular graph, they often put an extra parameter on it, namely the degree of every vertex. So then we call gamma k regular if the degree of every vertex is equal to k. And what I proved was that if your graph is k regular on n vertices and k is either very small or very big in comparison to n, then A gamma has the R-infinity property, of course, provided gamma is not a complete graph. And as I mentioned earlier, I also looked at strongly regular graphs. If it's strongly regular and connected, then it also has the R-infinity property, or the right-angle Tartan group has the R-infinity property. But both these results follow from previous results in the sense that for these values of k, your graph is either a disjoint union or a simplicial join of factors for which you know the R-infinity property holds. So it follows from the previous results, and the same thing holds for strongly regular graphs. So either they are transaction free or they are complete multipartite graphs, but these are simplicial joins of co-cliques. So again, in that case, it follows from the result on simplicial joins. So connected regular graphs, I've found some families for which the R-infinity property holds for the corresponding right-angle Tartan groups, but based on the fact that they have some additional structure besides regularity. So this I can be quite short about. Now, at last, for the final family, these max-bi-abelian graphs. At the moment I found this definition and these conditions on these graphs, I looked into the literature to see if this notion was already defined. I didn't find anything, so if any one of you recognize this definition in some extent, please let me know. I will be happy to see new results regarding this. But at the time, I just approached it as a new family of graphs and saw what I could do with them. So first of all, I introduced or I extended the definition. So a max biabelian graph, I added 3 parameters, n, k, and d. So n is the number of vertices, k is the size of the number of, or sorry, k is the number of vertices of maximal degree, and d was equal to the maximal degree of our graph. And as before, max biabelian means it's connected and non-regular. So k is strictly less than n, is what it means. And if we delete all vertices of maximal degree, we get a complete graph. And to give an example, this graph on 5 vertices has 4 vertices of degree 3, v1 up to v4. So n is 5, k is 4, and d equals 3. And if we delete v1 up to v4, we are left with a single vertex. So this is a complete graph, namely the complete graph on one vertex. So this is an example of a max biabelian graph. So they also exist. It's not that it was a condition that is never satisfied. But at that point, I first looked into some graph theoretical properties. So I looked at some conditions on these parameters k, d, and n, see how they are related. And I found a couple of inequalities, or we found a couple of inequalities. So the first one states that k and d can't both be small at the same time. Their sum has to be at least n plus 1. So either you have a very high maximal degree, or you have a lot of vertices of maximal degree. This is what the first inequality means. And the second is an upper and a lower bound on the number of edges you have. And I used this to prove the following corollary, pardon me, namely that an MBA graph, max biabelian graph, has, first of all, at least 5 vertices. And second of all, at least half of the vertices have maximal degree. So you have a lot of vertices of maximal degree in this case. And moreover, if equality holds, then you have an even number of vertices in total. But this bound on the number of edges. So we have some non-trivial structure on our graph, which I didn't really could exploit directly, but it gave me some intuition on how these graphs behave and what they look like, which could help in trying to prove the R-infinity for the corresponding right-angled Artin groups. Now, with the graph properties investigated to some small extent, I then looked at trying to prove the R-infinity property for the corresponding right-angled Artin groups. And as for regular graphs, I started with easy values for the second parameter k, namely big values of k. So k is strictly less than n, so the maximal value of k is n minus 1. So I looked at n minus 1 max biabelian graphs, and in this case, I could directly prove that they have the R-infinity property. So going back to the example I gave earlier, this was a 5, 4, 3 max biabelian graph, so this satisfies this condition. And how did I prove that it has the R-infinity property? Well, I've looked for a specific characteristic subgroup generated by vertices, and the one I found was the subgroup generated by the neighbors of your sole vertex of non-maximal degree. So the neighbors of V0 are V1 and V4. And if you take the characterization of characteristic subgroups by hand, you can check that the set V1, V4 satisfies the conditions. So rough ID, it's preserved under graph automorphisms. V0 has to be mapped to itself since it's the only vertex of non-maximal degree. So V1 and V4 have to be mapped among themselves because they are neighboring to V0. And with respect to this link is contained in star condition, V1 and V4 are the only vertices which contain V0 as a neighbor. So V2 and V3 can't be added to this collection by means of this condition. So V1 and V4 will induce a characteristic subgroup. So if we delete them, we obtain a disconnected graph with V0 on the one hand and V2 and V3 on the other hand. So any graph gamma, so A gamma has a characteristic quotient corresponding to a disconnected graph. So this quotient has the R infinity property, and we can lift it to A gamma itself to prove that these graphs has the R infinity property as well. So these cover the maximal case for MBA graphs. Now for K one less, so n-2, the situation is already more complicated. Here we have to have case distinction. So we denote the two vertices of non-maximal degree by V1 and V2. And then there are two possibilities. If it happens that V is a disjoint union of the neighbors of V1 and the neighbors of V2, so every vertex is either a neighbor of V1 or of V2, but not both, then your group A gamma has the R infinity property. And if it's not the case, then I didn't prove directly that it has the R infinity property, but I could reduce it to a smaller case. If it's not the case that it's the disjoint union, then A gamma has another right angle Tartan group A gamma prime as the characteristic quotient. And A gamma prime is not abelian as well. And it has strictly less vertices. So I've made my graph smaller. So it could help in an induction-like argument to prove that every right angle Tartan group has the R infinity property. Now, to give an example of both cases, for the first case, consider the graph on the left. So here V1 and V2 are the vertices of degree 3, which is not 4 as for the W named vertices. The link of V1 consists of the 3 white vertices, and the link of V2 consists of the 3 black vertices. So the conditions are indeed met. And how did I prove that this graph has a right angle Tartan group with the R infinity property? Here I used the notion of adding edges. So I used, instead of going to another graph by deleting vertices, here I add edges. And which edges did I add? I added the ones making this graph into a simplicial join of the white vertices and the black vertices. So I added all edges between the white vertices and the black vertices. No, in this case, they're all there. So it's already a simplicial join. And this was what I was working to, because it's a simplicial join of disconnected graphs. So the white vertices, V2 is linked to neither W2 and W3. So W1, W2, W3, and V2 forms a disconnected graph, the same for the black vertices. So it's a simplicial join of disconnected graphs. So by the previous results, it has the R infinity property. This is case 1, and in case 2, we have this type of graph. So here, both conditions fail. V1 and V2 have a common neighbor, this black vertex, and these two black vertices are neighbors of neither V1 and V2. So both of the conditions here fail, but still A gamma has a characteristic quotient that is non-abelian strictly as vertices. And I think the vertex you have to delete is, or you can delete, is this one. So the intersection of the neighbors of V1 and V2 gives us the set of vertices we have to delete in order to obtain A gamma prime. So here already we have some more difficulty. And for n-3, n-4, I didn't find any similar results because I didn't have any, or didn't have enough idea of the structure of these max biabelian graphs. But as it turned out, it was sufficient to prove the theorem mentioned in the beginning. So with what I've discussed in this talk, you have sufficiently strong results to prove the conjecture for all graphs on at most 7 vertices. This gives one way of quantifying, but as I said in the beginning, there are other ways. You have other infinite families of graphs on more than 7 vertices with right angle Tartan group having the R infinity property. And to give an idea, you can just take any graph in the green area of this rectangle. So disconnected graph, transaction free, or a simplicial join of certain graphs, or a graph lying in this shaded green area that reduces to one of the 3 cases. So there are 2 ways of quantifying these results. And as I said, so everything I've discussed here is enough to prove the result up to 7 vertices. And as I said, there were 59 remaining graphs we have to consider. I've given them here explicitly, and the graphs are colored using the same convention as after the simplification lemma. So blue graphs are disconnected, yellow graphs are connected, regular, and non-complete, and red graphs are max by abelian. And so every blue graph is covered due to the fact that we've proven it for all disconnected graphs. For the yellow graphs, the regular graphs, here the regularity degree is either very small or very big. So in this case, nothing truly spectacular can happen. And for the MBA graphs, it's always the case that there are either n-1 or n-2 vertices of maximal degree. So they are all covered by the results I mentioned earlier. Just to give an idea, our explicit way of seeing which graphs remain. But for 8 and more vertices, I don't know if I know there are examples for which the theory doesn't hold, but I did not find any new results in seeing what we can do for the remaining cases. Now, as a last slide, I would like to mention some similar and further research. So for further research, as I mentioned earlier, for regular and max by abelian graphs, I don't have yet an idea of how to tackle the remaining cases. My hope is that we can find suitable characteristic subgroups to go in the same fashion, even characteristic vertex subgroups as we did for max by abelian graphs. But especially for the latter type, the first step would be to see if we can exploit more structure from this max by abelian condition. So if anyone is looking for a new research topic, I could say go nuts on the MBI graphs if you want. So this for further research and similar research. Another, well, now PhD student, last year master's student of my supervisor, Martin Lathauer is he called, investigated the Reidemeister spectrum of two-step nilpotent quotients of right-angled Tauten groups. So for these quotients, you will have more options than just the R infinity property, in the sense that he discovered graphs for which the Reidemeister spectrum is either very big or very small. So there are more options. The conjecture is not that these all have the R infinity property. There are families which have the R infinity property, but also groups where the Reidemeister spectrum contains quite a lot of natural numbers. And just, yeah, you can ask the same question regarding the generalizations or related groups to right-angled Tauten groups. So what happens for arbitrary Artin-Tit groups, sorry, or for their associated Coxeter groups? What can we say about the Reidemeister spectrum or the R infinity property? And the same for the other generalization. So for graph products, take a graph and groups on every vertex, construct a group in a similar way as for right-angled Tauten groups. Can we say something about its Reidemeister spectrum, or do they also have the R infinity property? These are still open questions. So we're not done yet with this topic, but we can still try and look for partial positive answers. So this is where I would like to end. So thank you very much for your attention, both for attending this talk and my previous one. And if you have any questions, I will be happy to answer them. Thank you.
Thank you, Peter. So I have several questions, but before me, does anybody have some questions?
Yeah, I would like to ask Peter. Actually, I'm interested in your investigations concerning connected strongly regular graphs. And there is some theoretical results concerning what should be K, right? So it is something like a lemma in your presentation. So K should be from the set of 4 elements, 1, 2, n-3, and n-2. Right, yeah, right. Well, but you see, actually, there's a very specific, interesting case of strong irregular graph. It is exactly cubic graphs. So can you say something about this family of strong irregular graphs?
So for strong irregular graphs, it's independent on the value of k. So I've proven that for a strongly Lagrange graph, if it's also connected, then either it doesn't admit any transactions, or if it's not the case, then specifically it will be a complete multipartite graph.
Right. Yeah.
So I think in the cubic case, you can get examples of both families, either a complete multipartite graph or another one.
Oh, I see.
So
I
the reason I looked at strongly Lagrange graphs is I was looking for another family of graphs with stronger regularity conditions I could exploit, and I stumbled upon strongly Lagrange graphs. I don't remember how exactly, but I stumbled upon them and thought, well, let's see what happens. And I was surprised to see that this was a quite hard separation, in the sense that either it doesn't admit any transactions or all vertices admit transactions. So it was really 0 or 1, nothing in between. But for cubic graphs in general, if I recall correctly, I don't know an exact example, but I thought that there was some graph on 8 vertices that was not transaction free and even vertex transitive, but I'm not sure. So where things didn't work. I know there is an example on 10 vertices, but I don't think it's cubic. So
I see. Okay, and in the list, I mean, there was a slide connecting all, having all graphs. I mean, at the end of your lecture, it was a slide.
This one.
Yes, this one, yeah. So that is an answer to conjecture. So you said that all regular graphs are presented here, right? Yeah, and they are marked by yellow color.
Yes, well.
Right, yeah. So is it true that all of these graphs can be considered as Cayley graphs over some group?
Wait, regular Cayley graphs.
Well, Cayley graph means that you need to consider a group and to take some generating set, and then you can get a graph here.
Yes, indeed. It's been a while. I know the cyclic graphs are these cyclic graphs are the
definitely, yeah, right. Yeah.
For the other regular graphs, I have no idea. I haven't really looked into Cayley graphs. I know this is one natural way of going the other way. So starting from a group and associated to it a graph. I did wonder if going from a group and then to its graph and back, you will get right angle Tartan groups, what happens in that case, but things get very wild looking at the Cayley graph, so this didn't work out. But for the rest,
is it all these examples are Cayley graphs, I think.
Yeah. I don't know. I'm really not familiar with this theory, so I couldn't give you an answer.
Well, but are they vertex transitive? Do you know? They should be vertex transitive.
Yes, right? The yellow ones, not all of them are vertex transitive.
Brilliant. Well, this is the answer. If not all of them are vertex transitive, this means that if it is not vertex transitive, this means that it's not Cayley graph.
Yeah, indeed. I'm thinking, do I know one by heart? It isn't vertex transitive in this case. Where did I find the first one which is not vertex transitive? I think there was also in the cubic case on 8 vertices.
Really?
Yeah.
Oh, 8 vertices. I see. But here you have all graphs over 7 vertices, right? Yeah.
Well, I don't know if there is a non-vertex transitive regular graph here. I mean, for this one, I can see
it should be, yeah.
Clearly, and here I don't know because they're drawn using Python and it just takes any representation. So I don't really know. Yeah, sorry, I can't really give an answer to this.
Okay, that's all I would like to ask. Thank you very much.
You're welcome.
Thank you. Does anybody have other questions?
So, hi.
Hi, Sushil, please, you can ask.
Yeah, so, yeah, Peter, a nice talk. So I have
you.
just one question. So why this vertices at most 7? What is the use of that restriction on your theorem?
Because with 7, with what I've proven, I could cover all remaining cases on 7 vertices. But on 8, there exists cubic graphs on 8 vertices, and so regular graphs of degree 3. And for these graphs, I couldn't explicitly prove that they have the R infinity property, and they aren't.
Okay.
It's not possible to reduce them by deleting maximal vertices, because then you would delete everything. So I did look into this, and by trying every case by hand, I think I covered them all, and I could find arguments that they are indeed that they have indeed the R infinity property by either proving they are transaction free, or by finding manually a characteristic subgroup reducing the number of vertices. I didn't want to include this because first, I wasn't sure if I covered every case. And secondly, it would have been quite a lot of manual computation that I didn't really see fit for either my master thesis or an article to put into it. And it was also at the end of the year I looked into this. So time was a bit more scarce.
So like it's like accumulative, like all this step. If the number of vertices is at most 7, then this will fall one of this category, this blue triangle, the square. Okay. And I have one more question. So if I take any like finite index subgroup of this right angle Latin group where it has the R infinity property, then is it true that it is also has the R infinity property?
Very good question. I've been wondering it myself. If you look at finite index subgroup and it has the R infinity property, I don't know.
If it is not characteristic, then I believe that it's not true.
Well, I know this is very recent.
No, if it is finite index and then, okay.
If it's finite index and not necessarily characteristic, but it has the R infinity property, then your automorphism group has a finite index subgroup for which any automorphism has infinite Reidemeister number. So you're close, but not completely. But this is indeed something I've been wondering myself, and that would be very useful to prove our infinity properties for other types of groups if we could look just at finite index subgroups. But I share Timur's skepsis to some extent. If it would hold in general, this would be massive in this theory, but I think we have to put some more conditions on it. Because
so I asked this question because for one reason that if you have a right angle Latin group, then it contains at least right angle Coxeter group as a finite index. Probably I'm correct.
I think it's the other way around, that a Coxeter group contains a right angle group as a finite index subgroup.
Okay. It's other. Okay. Yeah. So my bad. Okay.
But it's still a valid remark in the sense that if this is the case, then this is the case. This has been proven. And if you then have the R infinity property for all right angle Tartan groups, then you could prove it in some way for Coxeter groups if you could lift it from finite index subgroup.
Yes.
But of course, then you have to prove that you can lift this, and I don't know if it's true in general. Perhaps for these types of group, you have enough structure to prove it, but I have no idea if it's true. So.
Okay. Yeah. No problem. Okay.
But it could be useful.
Okay. Thanks, Peter. Yeah.
You're welcome.
So, I think that we have time for more questions. Does anybody have any? Because I have quite general question. Okay, I will ask. What should be the next, the following strategy? Because what I see is now just take some graphs from some families. What I see is the Z-graphs, which are studied in Novosibirsk, and try to understand, try to find some graphs which don't belong to any families you consider, and try to prove the R infinity property for these graphs. Is it the idea which you recommend to follow, or I mean, how to finish this conjecture?
There are two ways. The first one related to what I've done here is so the remaining cases are MBA graphs and certain regular graphs, or just take regular graphs. I mean, there are this is the result I've proven here are not that big for the whole family of regular graphs. Now, on regular graphs, this was one idea I had, but I didn't really work out, is this notion of, wait, where did I put it? So this relation, if you view this as a relation on your vertices, on a regular graph, this is an equivalence relation. This is also called that V is dominated by W, so being dominated as a equivalence relation on regular graphs. Pardon me. With this, you can look at the equivalence classes, and then any characteristic subgroup generated by vertices is in fact generated by one or more equivalence classes for this relation. So you have more structure on how these equivalents or how these characteristic subgroups work. And if I recall correctly, but it's been a while since I looked into this, I will come to that later. There are three possibilities. Either there is only one equivalence class, then your group is vertex transitive. And I think, but I'm not really sure, that the proof I gave for the disconnected case can be modified to work for vertex transitive case, because your automorphisms will have a strong resemblance to the case for disconnected graphs. So I should mention here that for disconnected graphs, I first reduced to the case where you have a disjoint union of complete graphs. And for vertex transitive graphs, the way it looks is you have certain clusters, namely your equivalence classes of this this relation, and then two classes are either joined completely or not at all. So it looks like a graph product. Like it looks like from far, it looks like a graph where each vertex is replaced by a bunch of vertices. And this strongly resembles the way a disconnected graph of, or a disjoint union of complete graphs works. So I think in the vertex sensitive case, you can modify this proof, but this proof was already quite long and technical, and with ugly notation. With the vertex sensitive case, it gets even worse. So this is the first case. For the second case, I think you can find a non-trivial characteristic subgroup with a non-abelian quotient, so that you can work by induction. But there is a third case where nothing like this works. It's not vertex transitive, but every characteristic quotient is abelian, so that you are in no man's land in between the two IDs, so that none of the techniques really works. And that's where I'm stuck. I didn't really see an additional approach. And for max by abelian graphs, I don't have any idea if I can exploit structure in a clear way, because my hope would be that in some way I can extend this argument that if it's n-3, then and there are two cases. In the first case, it's directly provable, and in the second case, we can reduce the number of vertices. But since it's already quite technical or long in this case where n-2, my hopes are quite low for n-3 and so on. So this is first approach, namely really look at them as groups associated to graphs. The second approach is what I'm in some vague way doing for my PhD, is losing the information that it comes from a graph and trying to find true group theoretical properties that could imply the R-infinity problem. Right angle Tartan groups that are non-complete all contain a free group as both a subgroup and a quotient, because you can just take the two vertices that are not connected. The subgroup they generate is a free group of rank 2, and you can delete all other vertices to get them as a quotient. And this is more a true group theoretical property, namely having a free subgroup. And perhaps this is strong enough to prove the R infinity property in general. I have no idea if it's true, but this, if I were to look into this problem now and try to solve it, I would do it in this approach, because then you get some results like this one, where you use truly group theoretical properties and not the fact that you come from a graph. But of course, this is just speculation. This is what I would do. I really don't know if it will work in this way, because I've been doing other research for the past couple of months and the past 2 years. But this is, if I were to go back to this, I would try to do it in either of both ways. So if anyone can give me some, for instance, more information on max biabelian graphs and some structural properties, perhaps this is sufficient to solve this case.
I didn't expect so detailed answer. So thank you. Thank you for the answer, and thank you for the talk. We are very grateful that you agreed to give these lectures.
Thank you. I'm very grateful that you asked me to give these lectures.
Yeah. So
thank you.
Your slides, I will ask you to send it to me, and the video will be available on our website.
Okay.
And I will let you know about it.
Okay, thank you very much.
So thank you, everybody, and we are finishing here.
Thank you, Victor. Yeah, it was great. Yeah, thank you.
Thank you. You're welcome.